In this lecture, I will present Grover's search algorithm. This is one of the most important algorithms in quantum computing, and it is also known as amplitude amplification algorithm. I will present what the search problem is that this algorithm is trying to solve, and we will then discuss its classical solution and then present Grover's algorithm for its solution. We will see that Grover's algorithm can solve the problem on a quantum computer uh, polynomially faster than on a classical computer. So let me share my notebook and discuss this problem. So let me start by defining the problem. So we have Grover search problem, and the problem is this, that suppose we have an unstructured database and we want to find an entry. Suppose there are some items in it, at item 1, item 2, and so on, and they have some index as well. So suppose this item is index 0, the next item is indexed 1, the next item is index 2, index 3, and all the way up to n minus 1 index, where total entries in the database are n. And suppose we are trying to search through this unstructured database, that it's not sorted or anything, and we want to find a particular item. And then suppose there is an oracle that have access to this database. Let's call this oracle UF. And if we input this index to this oracle, let's say I send in 2, and it can go and find out what's the item corresponding to this index, and then tell us whether this is the item that we are looking for or not by giving a minus sign with it. If this is the item that we are looking for, it will put a minus sign, and if this is not the item that we are looking for, it will put a plus sign. So it means in quantum term, this oracle UF, when it operates on some input x, it gives it a minus sign if the input is the item that we are looking for. Suppose the item that we are looking for is W, and it gives the input as it is on the output if the index is not of the item that we are looking for. So this UF oracle has access to this database, but as far as we are concerned, we are only giving it some input, and it's giving us the index as input and index as output. And by identifying the sign in front of this, we're able to see whether this index is of the item that we are looking for or not. And just for ease, let's say there are total of capital N items, such that the number of bits that we need to uh, give this index are n, small n. So there are n bits of input in binary, and their total number of items are 2 power n. Okay, so this is the problem, that we have to find an item in a database, and the database is unstructured. So let's see what's its classical solution is. So classical solution, since the database is unstructured, actually we can't really think of any efficient algorithm. There's only or you can search randomly, or maybe you can search one by one. The number of queries that are required to search this item in the worst case are the same. So suppose we can, select this 0 and give this 0 as input and find output. Then we give 1 as input and check its sign and so on. So in the worst case, we might have to give all the indexes as input to see which one of the item is the item that we are looking for. And if we are lucky, and if let's say we give this entries randomly, the entry that we are looking for might be found earlier. But in the worst case, so worst case complexity is that we will have to give n queries to this oracle to find our item that we are looking for. Okay, so the classical algorithm requires n queries, and what Grover found is that this problem can be solved much faster on a quantum computer. So Grover's theorem was this, that we can solve this algorithm with just number of queries of the order n square root to this oracle instead of n, if we have access to a quantum computer. And the statement of the theorem is this, that we start, let's say, our qubits in state 0, all of them, and apply Hadamard. So we have n qubits, small n number of qubits, and they're all initialized to 0. And we apply Hadamard to each of the qubit, and then we pass this superposition output from the Hadamards to this oracle UF, and then there is a special reflector function found by Grover. Let's call it V. You apply this reflector. I'll describe this one later on, and then you repeat it R times, repeat R times, and then measure it. And the theorem says that the probability of finding the required W is very high, almost close to unity. So let's prove this. Let's find out whether this theorem is true, and in along the way I will also define what this V is. Okay, so let's start step by step and go through this circuit. So let's start with the initial state. So initial state is let's call it some psi 0, is that all qubits are in 0 state. And this tensor n means that we have n qubits. This essentially is this state where we have n zeros in this state. Or if you want to feel more comfortable, you can actually express it like this as well. So we have 0 initial state, and let's see what's the state after the Hadamard transform. This act of applying Hadamard gate to each qubit is called Hadamard transform. So let's call the state after Hadamard as state S. So the state S, I'm calling it S because Hadamards prepare superposition states. So S is basically Hadamard applied to each qubit. And we can also represent it as a shorthand notation like this. Okay, and we know that Hadamard transforms zero state into plus state, so we essentially have plus states on each of the qubit. And if uh, we express it in more detail, let me write this plus as 1 over square root 2, 0 plus 1, tensor 1 over square root 2, 0 plus 1, tensor so on, and the last one is this state. Now let's go to the next page. The S state essentially has 1 over square root 2 multiplying n times, so it's power n, and then we have 0 plus 1. There's a tensor everywhere, and 0 plus 1. So this coefficient I can actually write it like this as well, 2 power n square root. And now we have first term, let's say this 0 tensors with this 0 with this 0 and all the zeros. And then next term could be 0, 0, 0 all the way here, and then this 1. And then the next term would be 0, 0, 0, 1, 0. Let's say I'm working with 5 qubits. And then the last term would be 1, 1. Now we can introduce a shorthand notation. So this is just capital N. Let's call this state just 0 for the sake of writing it easily. And let's label this state as 1. Let's label this state as 2. The next state 3. All the way to the last state, which is n minus 1. And this is our equal superposition state. Now, before I actually move to the next step, let me, sort of jump ahead a little bit and say that, these are all possible states, and one of these states is the state that we are looking for. And suppose that state is some state labeled W, and let me just separate it out. So let's just separate out so I'm putting 0 in place of here, and then n minus 1, and this W I'm just writing it separately, and we don't have to forget this 1 over n square root that is here. So this is here. So basically I took the W out from here and took it there on the separate. And now we can easily see that this is not a normalized state because I have one item less, and then here it's 1 over n square root. And just to let me put an n minus 1 square root here and an n minus 1 square root here, and then this is 0 plus 1 plus 2 all the way This is a state that doesn't have this W state, and then this. And let us simply call this state as a state W perpendicular, because this is indeed perpendicular to state W, because there's no W state in here. So if you take inner product of this state with W, you will get 0, because this W is orthogonal to each of the other state, because this is essentially taken out from this sum. So this means that we have been able to write our initial state, our superposition state S, as just a superposition of two normalized states like this. So this W is already normalized, and we have normalized this W perpendicular state as well. This is some coefficient. And since the square of this and square of this is equal to 1, what I can easily do is define this state as cosine alpha, and define the next state, next coefficient as sine alpha, because their square will be 1. So if I have a plane in which I can represent this higher dimensional state in just using 2 dimension. So let's say this is W perpendicular axis and this is W axis, and our state S is this state, and it has some angle alpha with this W perpendicular axis, because there's a cosine alpha here. Alright, so now we have been able to see what our S state is, and let's go back to the original circuit and come here. So you see that we have been able to work out what the state is here, S. Let's now apply this UF and find the state right after UF. Let me call this state as some SF, because this is a state that is obtained after applying UF. Alright, so before I apply UF, let me just spell it out again what UF is. So UF is a function that if you give it a state W, which is actually the solution that we are looking for, it gives us the answer minus W. And if I input it any state other than W, I get the same state out. So this is when X is not equal to W. It means even the sum of all of the x's, so let's say sum of 0 plus 1 plus 2, and there's no W state, okay, so I'm just putting a 0 to indicate that the W state is missing. So all the way to n minus 1, I will get the same state out as it is, because none of these indexes belongs to the solution state that we are looking for. So this by definition is an oracle that only put a minus sign if the input state is the state that is our answer. So this means actually that since this W perpendicular is nothing but this sum, divided by this. So this W perpendicular is actually this sum divided by this constant n minus 1 square root. So since constant don't play a role in here, I can just write it like this. So it means that UF is a special operator that gives a minus sign if the input is W, and it gives the plus sign if the input is W perpendicular. And W perpendicular is sum of all of these states that are not W. So this means I can easily express this UF like this, that this minus this. So this is an operator that does exactly what we just described. All right. And I can easily write it like this. Let me just uh, add one W perpendicular operator and subtract it again. So I added and I subtracted the same term. So when I added, so it just added into this part, so this becomes 2, and I just subtracted this over here. So this I can write, let's write here, 2 W perpendicular minus identity, because identity is this matrix and this two-dimensional Hilbert space spanned by W and W perpendicular. Identity is just this matrix, because in this basis W and W perpendicular, this is this. And now if we look closely at this UF operator, this is nothing but a reflection operator. Okay, so it means that if I apply this UF operator to our S state, it will simply reflect it around this W perpendicular axis, which means that I have this state S over here, and after reflection around this axis W perpendicular, this would become a state like this, making same angle alpha, and let's call it SF. So this is nothing but cosine alpha W perpendicular minus sine alpha W. You can work it out in detail if you want, but since in just the last lecture I described how reflection operators work, and this operator has exactly the form of the reflection operator, reflecting around W perpendicular axis. So after reflection around this W perpendicular axis, S state becomes SF state. Perfect. So this means that let me just go back here to the main theorem. Said that we have been able to find state at this position SF, which is just a reflection around W perpendicular. Let's now find out the state after operator V, and let me call it some S prime state. So S prime state would be, so S prime is operator V applied to SF state. And just to recall, so in the W perpendicular W plane, state S was here making angle alpha, and state SF was here making angle alpha on the negative side. So this V operator operating on state cosine alpha W perpendicular minus sine alpha W. And let's now define what this V is. So Grover actually came up with this idea that let's take V to be this operator, that this is an operator that reflects the state around this axis. So this is an operator that will reflect this SF state around the S axis and take the state over here. So S prime after this V operator would be, since this is this a reflection operator around S axis, and let's call it some S prime, and you can see since this is angle 2 alpha, so SF is making angle 2 alpha with S, so after reflection it should be making angle 2 alpha over here, and the total angle with this axis would be 3 alpha. So S prime state would be cosine 3 alpha minus sine 3 alpha W. So this was the key, contribution by Grover, that designing this V reflector to reflect around this state S. So now after one pass through this Grover circuit, so let me actually redraw it. So in a shorthand, so what he did, he applied this Hadamard transform on all n bits, and then remember these are n bits that I'm talking about. So initial state is this. So these are also n bits. So after applying the Grover operator, he applied this, after applying this oracle UF, he applied this Grover reflector V, and then we got this n qubit state. So the state over here we have called S, the state over here is SF, and the state over here is S prime. Now let's repeat it. So what we are going to do is going to apply this UF again. So in circuit terms, actually you can imagine that this UF is coming again, and then V would come again. So we are exactly going to repeat this block. So let me do it here and write the output directly. So suppose we have this plane again. So now our state over here is S prime. So this is S prime and it's making angle 3 alpha. So when we apply this UF again, so our state will be reflected around this omega perpendicular axis, and we'll go to this SF prime. So this is again 3 alpha, and then when we apply V, this V is always going to reflect around this state S. So with S, so since this angle was alpha and this angle is 4 alpha, after reflection our new state, let's call it some S double prime, is going to make angle 4 alpha over here. So total angle with this omega perpendicular would be 5 alpha. So alpha angle of S state, and then 4 alpha angle of our new state S double prime with S. So S double prime would be cosine of 5 alpha. Let me just write it actually, alpha plus 4 alpha minus sine of alpha plus 4 alpha, because now our S prime state has this angle 4 alpha plus angle alpha with this W perpendicular axis, so it becomes cosine of this. And if you do this R times, that we repeat this UF and V operation R times, and let's call it this state SR. So we get cosine alpha plus 4 sorry, not 4, but since each time we are adding 2 alpha angle to our state, so this okay, so this must be plus sign because we are on this side, so this is plus sign as well. Sine alpha plus 2 or alpha w. So this is the state after uh, our applications of UF and V operators. And what we want is that at the end of our iterations, let me just show it here again. So let's start from here. So initially our state after first Hadamard transform was S, making angle alpha. After first application of UF, it becomes SF, making angle alpha here. And after first application of V operator, the state became S prime, making an additional angle 2 alpha with S state, because this SF got reflected around X. So SF is making angle 2 alpha. So after reflection, it's making angle 2 alpha on the other side. And after second application, S prime was reflected again. So UF always reflect around omega perpendicular. So this angle is 2 alpha plus alpha. So it came here. So this SF prime. So this was 2 alpha. And after second application, so it became S double prime, making angle 4 alpha with 2S. So an additional 2 alpha with respect to S prime, and so on. And after our iteration, our state has come here, maybe not exactly W, but close to W. And this SR state was cosine alpha plus 2R alpha W plus sine alpha plus 2R alpha W perpendicular. And we have to choose this R very judicially, and that we can easily do that. Let's choose this alpha plus 2R alpha such that this angle after R applications becomes pi by 2, because, or at least near pi by 2, because at that stage when this condition is satisfied, this SR state would be nearly okay, I think I made an error. So this is perpendicular and this is perpendicular and this is not. Okay, so after our application, since cosine pi by 2 is going to be roughly 0 when this angle is near pi by 2, and the sine of angle near pi by 2 would be approximately 1, and this would be approximately W, and what we would be getting is this state. So let's compute R from here. So R would be 2R alpha is equal to pi by 2 minus alpha, and let's divide by this 2 alpha on both sides. So R becomes pi over 4 alpha minus half. So this is the value of R, and since this R in general is not an integer and we have to use only integer repetitions, if you can always round it off to lowest integer. For example, if it is 3.2, we can take 3 iterations, because that means that 3 iteration will get us closer to this W axis. And when n is large, when n is large, and by the way, I didn't specify what alpha is. Alpha, if you recall from the very first appearance of alpha, alpha came here. So this was where alpha was defined. So cosine alpha is this and sine alpha is this. So sine alpha is equal to 1 over n square root. So let's come here. So alpha is sine inverse 1 over n square root minus half. So when n is large, I can approximate alpha like this. So sine inverse 1 over n square root. And when this n square is large, so it's going to be approximated with just 1 over n square root, and in that case r would become pi over 4 1 over n square root, and I can forget this half in this case, so this would be n square root pi by 4. So we can see that the complexity of the algorithm is n square root, that the number of queries to the oracle scale as n square root, not n as in the classical case. So this was the key algorithm that showed that the quantum computer can solve the search problem with n square queries to the quantum oracle, accessing the unstructured database than the n queries. So there's one last point that I still need to address, and that is how to implement V, or how to work out the circuit for V. So let's do that now. Circuit for V. So remember, V was a reflector around S axis. So this was defined like this, and where this S was the equal superposition state that came out after applying Hadamard transform to qubits initialized in 0 state. So this was the S. So it means I can now write this V as 2 Hadamard on 0 state, and then it's dagger minus identity. But we also know that Hadamard is its own inverse. So I can write identity as simply Hadamard square, Hadamard and n bit Hadamard times n bit Hadamard. Because this is a product, this is not a tensor product, this is just a product because two Hadamards are applying on each other. But now I can take Hadamard common from left, and Hadamard common from right, and I'm left with identity in the center again. And this, if you recall, is another reflection operator. It reflects around 0 axis. So Hadamard U0, let's call it U0 Hadamard. So we have the circuit, the total circuit for the algorithm like this now. So let me actually add a page. Now the full circuit is this: Hadamard, Hadamard, Hadamard's on all qubit, initialize in 0, and then Oracle UF, and then the V operator. And V operator actually also have Hadamard's on all qubits, and then a reflector U naught, and then a set of Hadamard's, and then we have to repeat this circuit R times, and then do the measurements, and our output probabilities or output histogram would be something like this, that for all possible outputs like 0, 1, 2, 3, 4, some W, and the last one and -1 would be something like the other states have a small probability, but the state that we are looking for would have a large probability of measuring, because after R repetition the states have come over here. Okay, so this concludes our introduction to Grover's algorithm, where I try to present it in a simple manner using only reflection operators, which we introduced in the last video. And we saw that the Grover algorithm essentially operates by starting an equal superposition state, and then at each iteration it moves the state closer towards the desired solution. And actually there's an alternative view of this algorithm as well, where we can imagine this algorithm as an amplitude amplification algorithm, where we can think of UF as marking the state with a negative sign, and then the V operator increasing the amplitude of the desired state. So in the next video, I will show how to implement this algorithm in Qiskit, and there we can see how to compute the number of iterations, and how to implement the circuit and run it on IBM quantum computers.